Okay, so now we'll be doing topic 4.3.3, which is action and use of circuit components. Now, this one mostly has explanation of different uses of circuit components and how they're set up for specific purposes to achieve specific purposes. There's only one bit of sort of mathematical work over here. So right, we'll take a look at that if it's makes sense. Otherwise, we can always go to the whiteboard. So I'll be using the text for this explanation. And the first thing they mention over here, which we've covered, I believe, yesterday, is the increase in the resistance of a conductor when the temperature goes up. Right, and that's because the atoms in the conductor vibrate faster and it becomes more difficult for the electrons to move through the material. And this means that the resistance of the metal increases. Right? So that's for an ohmic conductor, the temperature rises, the resistance increases. Now, when the resistance of the ohmic conductor, which follows Ohm's law, so V equals to IR, right? If the resistance increases and if a constant current is to be maintained, so if you want to supply a constant current to that component or to that circuit, right, then the potential difference also needs to be increased across the conductor, right? That is if a constant current is to be maintained. Otherwise, if the resistance goes up, right, your current value will fall if the potential difference remains the same. Then something we saw yesterday is the graph for the filament lamp, and we saw that it follows the ohmic path of a linear curve, but when it gets hot, it sort of curves and flattens, right? And that's because of the increased resistance as the filament heats up. Then here they're talking about a variable potential divider. So potential divider is a device that can split the potential difference, right, across different like components or branches of a circuit. So the resistance of materials other than metals do not necessarily rise when their temperature increases. In some cases, a temperature increase, such as a semiconductor thermistor, the resistance actually decreases when the temperature increases, right? So it's not the same case for all conductors. So if this thermistor is part of a potential divider in a potential divider circuit, then its resistance decreases as the temperature rises, right? That's how it works. The combined resistance of two resistors then decreases, right? Instead of increasing, whoops. So, right, instead of two resistors in series, right, the resistance increasing, it will decrease because as the temperature increases, the resistance of the thermistor goes down. So if the supply voltage remains constant, the current will increase. Why will it increase? You look at V equals to IR, right? That is I equals to V over R, right? I equals to V over R. So if resistance is increasing, the denominator is increasing, and the voltage is the same, the current will go up. Okay, simple math. This means that the potential difference across the fixed resistor increases relative to that across a thermistor. Why? Because a fixed resistor, it gets hot, the temperature and the resistance increases. So it's like a regular material. It's not a semiconductor thermistor that's going, has decreased resistance with temperature. So the potential difference across the fixed resistor could then be used to monitor temperature. The higher the resistance there is across a fixed resistor, that means the hotter it is, right? So that could be used as a temperature monitor. A variable resistor can also be used as a potential divider. Moving the contact on the resistor changes the output. So we had an illustration for this in one of the on earlier pages. If I can just go back and find it. Right here, I believe. Right, so you've got the potential divider. So a variable resistor can be used as a potential divider. Right, and so we talked about that earlier over here. Okay. Now, how do we, measure resistance and voltage and everything in a potential divider? So in the circuit shown in figure 4.3.13, so let's take a look at that. This thing, right? This is a potential divider circuit. Right, so you've got voltage coming in, current is flowing in a clockwise direction, so going up and then down. You've got two resistors over here. Right, the two resistors R1, R2 are in series with a supply voltage. Right, and the current in the circuit is, right, supply over total resistance. So V over R1 plus R2, because the total resistance is the sum of resistance, right? And the voltage is whatever the supply voltage, and so you get that current. And so the voltage across R1, right, what's the voltage? Because we know in series, right, the voltage is split between the different components. So what's V1? Right, and V1 equals to I, which is the same in a series, so the current remains the same in a series circuit, multiplied by R1. If we sort of fit that in, right, so I into R1, right, and what is I? I is V over R1 plus R2. So this becomes V over R1 plus R2 multiplied by R1, right? And so you can write that as the voltage, right, is R1 over R1 plus R2, right? So the individual resistance over the sum of resistance. And similarly, the voltage for across the second resistor is similarly, right, voltage multiplied by the second resistance, the resistance of the second resistor divided by the sum of the resistances. And so you can take a ratio of these, and when you do V1 over V2, right? And so I guess I'll go to the whiteboard for a bit of clarity for this. Right, so here we are. And so I'll just quickly write down, this is 4.3.3. And so, right, V1, right, or just is R1 over R1 plus R2. And V2 is R2 over R1 plus R2. So I hope you followed how we got to this stage, right? So if you take a ratio of these guys, we take V1 over V2 equals to R1 over R1 plus R2 divided by R2 over R1 plus R2. And you can sort of simplify that and say V1 over V2 equals to R1 over R1 plus R2, right, multiplied by R1 plus R2 over R2. And obviously these guys cancel out. And so you are left with a ratio V1 over V2 equals to R1 over R2. Does this make sense?
Yes.
Right, so the ratio of the voltages across these resistors is equal to the ratio of resistances. So, right, if you have, let's say, right, a resistance of, 10 and 20, and so that's a total of 30. And so 10 over 20 is 1 over 2, right? And so let's say you've got like a 6-volt supply, and so you split that 1:2, and so that will become, right, 2 volts going to the first resistor and 4 volts going to the second resistor, right? So you can use the ratio of the resistances to figure out how the voltage is being, so how much voltage each resistor is utilizing. All right.
Yes.
Okay. Coming back. So if that's clear, right, I did say we'll do numericals. I think we'll do a few the next time. I guess, right, with all of this covered, now we're just going to talk about, some different electrical components and how they're used. So we've got light dependent resistors, right? And the more light that falls on, the semiconductor cadmium sulfide coating over here, the resistance decreases. So it shows over here a circuit where you've got a light dependent resistor, and the more light that falls on it, the resistance falls, right? The current flows through, right? And so in this case, the lamp lights up, right? When the light from a lamp falls on the window of the LDR, so over here, its resistance decreases and the increased current lights up this lamp. So the source of light falling on the LDR is not this lamp, but from somewhere else. LDRs are used in photographic exposure meters and in series with a resistor to provide an input signal in switching circuits such as light operator intruder alarms. So what happens in light and operator intruder alarms, right? If the light is turned on and it falls on, the LDR, the light dependent resistor, right? As the light intensity falling increases, the resistance decreases, and that allows current to pass through the circuit and the alarm goes off. Okay, they're talking about how an LDR can be used with a relay. This is a circuit diagram of an LDR, right, an intruder alarm over here. And so how it's used in a relay. We'll talk about relays first and see if we can make sense of it. Then comes a thermistor. So a negative temperature coefficient thermistor contains semiconducting metallic oxides whose resistance decreases markedly when temperature rises. So the point to note over here is that temperature rises, resistance decreases. That's what you need to know. Okay, in a thermistor, the temperature may rise either because the thermistor is directly heated or because there is a current in it, right? Whatever causes the rise in temperature. Figure 4.3.15a shows what a thermistor looks like. This shows the symbol for thermistors over here. You've got this rectangle with a diagonal and then a straight line, sort of like a crowbar, right, in a circuit to demonstrate how the thermistor works. So as it gets hot, the resistance falls and allows the current to pass through. The lamp lights up, right? A thermistor in series with the meter marked in degrees centigrade can measure temperature, right? This is used in series with a resistor and can also provide an input signal to switching circuits. So they haven't explained what switching circuits are, right? So just something like, okay, fine, right? That's something. And being used with a relay. So let's talk about what relays are. They've shown it over here. A switching circuit cannot supply much power to an appliance, right? So a relay is often included, right? So just for clarity, a switching circuit is an electrical circuit designed to control the flow of current by turning components on or off, or alternating between, the on and off state, on and off modes. So basically turning stuff on and off is a switching circuit, right? So a switching circuit cannot supply much power to an appliance, so a relay is often included, right? So over here, so this is output of switching circuit. You close the switch, right, and you allow current to flow through, and so it's applied to it, it's connected to a relay. This allows the small current provided by the switching circuit to control the larger current needed to operate a buzzer as in a temperature operated switch or other devices. Okay. Relays controlled by a switching circuit can also be used to switch on the main supply for electrical appliances in the home. So figure 4.3.16, that's over here. If the output of the switching circuit is high, right, 5 volts, a small current flows to the relay which closes the main switch, right? So if the voltage is too high, right, it closes, it shuts it off. If the voltage is low, it opens again, right? So the relay also isolates a low voltage circuit from the high voltage main supply, right? So that, it doesn't burn things out. Now, if we take this understanding, that's a secondary control basically, right? To the supply to whatever circuit you set up. And we go and look back at the use of LDRs in a relay. So this setup over here, it shows how an LDR can be used to switch a relay. The LDR forms part of a potential divider across 6-volt supply, right? And this here's the LDR. When a light falls on the LDR, the resistance decreases and hence the voltage also decreases. There is a corresponding increase in the voltage across the resistors, right? Because notice over here that this thing is in parallel to this power supply, but within that parallel branch, the light dependent resistor and the fixed resistor, right, are in series. So there are two components connected over here. And so does it correspond? And so between these two, the voltage will drop, right? It will be split. So when the resistance falls over here, the voltage increases over here. When the voltage across the relay coil reaches a high enough potential difference, it acts as a switch and the normally open contacts close, allowing current to flow to the bell which rings. Okay, so the way this is working, right, this light falls, resistance falls, right, voltage falls. Voltage increases over here, that moves to the relay, right? If the voltage across the relay is high enough, this switch, the relay switch closes, it allows current to flow to the bell, right? And the bell rings. If the light is removed, the potential difference across the resistance and the relay drops below the operating, right? So in this case, perhaps 5 volts or whatever it may be. So that the relay contact opens up again, right? So the relay switch opens up again, breaking the circuit, and the bell is cut and stops ringing. Is this making sense?
Yeah.
Okay, that's good. Now a thermistor, right? How is that used as a relay? So figure 4.3.15C, let's take a look at this. You got a thermistor. As the temperature increases, it's basically the same thing, right? Instead of light, you've got a thermistor, and as the temperature increases, the resistance drops over here, right? So the voltage drops over here, and right, voltage increases here, which goes to the relay, which causes the switch to close and the bell to ring. If the voltage drops, the resistance high over here, the switch opens up, the bell stops ringing. Right? So it shows how a thermistor can be used to switch a relay. It forms part of a potential divider across a DC source, right? When the temperature rises, the resistance of the thermistor falls, and so does the potential difference across it. The voltage across the resistor R and the relay increases. When the voltage across the relay reaches its operating potential difference, right, the normally open contact closes, the circuit is complete, the bell rings. If a variable resistor is used in the circuit, the temperature at which the alarm sounds can be varied, right? So if instead of fixed resistor, you use a variable resistor over here, and so, right, if you want the bell to go off at a lower temperature, you keep the resistance low and it will sound off earlier. If you want the bell to go off at a higher temperature, for example, it's in the kitchen, right? For example, and obviously the kitchen's hot, and so you don't want the bell going off all the time, and so you keep it at a high temperature. And so when there's more voltage, higher voltage across this thing, then only the circuit will close and the bell will ring. Right, then two other things to talk about are the light emitting diode and the semiconductor diode, and then we'll be done with 4.3 as well. So the next time we can talk about electrical safety. Right, so let's do this as well.
We are gonna do the numericals now.
Huh?
Are we gonna do the numericals as well?
I sort of it slipped my mind, to be honest. When I started off, I did say that we're going to do numericals first, but since I started off with this, just remind me the next time that we have to do numericals for the part we covered in the last session. So we'll do that first so we can sort of cement the concepts of the parallel and series circuits that we talked about, and then we'll move on to electrical safety. So just do remind me in case I forget the next class, right? It slipped my mind at the moment, and so I only recalled it after I started explaining stuff. And so I thought, okay, let's just go on with this. We can do it next time.
Okay.
Okay, unless you want to do it now. I don't think I
Mm,
don't I don't think that's the case, is it?
mm,
Okay, an LED, right? So we're all familiar with LEDs. They're light emitting diodes, right? It's shown over here in figure 4.3.17a is a diode made of a semiconductor gallium arsenide phosphide. When forward biased, right, with the cathode C connected to the negative terminal of the voltage supply, right over here, cathode C to the negative to the voltage supply, negative terminal, right? So cathode C to the negative terminal of the voltage supply. The current in it makes it emit red, yellow, or green light. No light is emitted on reverse bias, right? Which means when the anode A is connected to the negative terminal. So if you connect it the other way around, right, it's not going to emit any light. If the reverse bias voltage exceeds 5 volts, it may cause damage. In use, an LED must have a suitable resistor in series with it. In series, right? So you've got like this and this, so there are no branches, it's all one. For example, 300 ohms on a 5-volt supply to limit the current, right? For example, 10 milliamps. And right, this figure B shows a circuit for an LED in demonstration. Right, so this is the symbol for an LED. You've got a triangle and a line at the tip of the triangle. Uh, let's say perpendicular line to the tip. LEDs are used as indicator lamps on computers, radios, other electronic equipment. Many clocks, calculators, video recorders, and measuring instruments have 7-segment red or green numerical displays. Each segment is an LED depending on which have a voltage across them. The display lights up the numbers 0 to 9. Right? So for example, this display over here, right? This whole thing is an LED. Depending on where the current's coming in, you can see these different numbers. The voltage, sorry, not current. LEDs are small, reliable, and have a long life. Their operating speed is high and their current requirement is very low. Diode lasers operate in a similar way to LEDs but emit coherent laser light. They are used in optical fiber communications and transmitters. And you're like, okay, fine, right? If you say so. Finally, we have a semiconductor diode. So a diode is a device that lets current pass in one direction only, right? And so the symbol for a diode is again a triangle with a thicker line perpendicular to the tip, right? So an LED has a thin line and it has these two arrows as well, of course, right, that are pointing away from it diagonally, and the diode has this thick line and a circle around it. So these are symbols that, right, you need to know. So it allows current to pass only in one direction, right? So this is what diode looks like, and this is the circuit symbol for it. And you may come across the symbol without the outer circle, right? So just a triangle with a thick perpendicular line at its tip. The wire nearest to the band is the cathode. So over here, right, this band, so this is the cathode, and the one at the other end is the anode, right? So the cathode is the negative terminal, and the anode is the positive terminal. The typical IV graph is shown in figure 4.2.29b, right? So we'll have to go back for that, right? For a diode. The diode conducts when the anode goes to the positive terminal of the voltage supply and the cathode to the negative terminal. It is then forward biased, its resistance is small, and the conventional current passes in the direction of the arrow on its symbol. If the connections are the other way around, so if the anode is connected to the negative terminal and the cathode is connected to the positive terminal, right, then it's reverse bias, the resistance is very high, and it will not allow current to be conducted. The lamp in the circuit shows when the diode is conducting. So I think they're talking about over here. Yeah. Right. So you can see the anode is connected to the positive, the cathode is connected to the negative, and so, right, forward bias, the lamp is lighting up. Over here, the anode is connected to the negative, so that's not what we want, and so this is, right, a reverse bias, and so there's no current flowing through, right, and so the lamp is not lighting up. It also acts as a resistor to limit the current when the diode is forward biased. Otherwise, the diode might overheat, right, and be damaged. A diode is non-ohmic, so it doesn't give you a linear line, right? Well, linear line, it doesn't give you a linear graph, linear line, line. It is useful as a rectifier for changing alternating current to direct current. Okay, so this is alternating current, and it doesn't let it alter to the other side. It just keeps it in flowing in one direction, right? So we know alternating current, the direction changes, and so we get this sort of wave-like, right, pattern for its voltage. But because the diode only restricts flow in one direction, it doesn't let it go in the other direction, and so it limits it to one direction and sort of makes it direct current. Even you're not getting like a flat line or a linear line or something, but it keeps it flowing in one direction. So that's why it's direct current. Otherwise, it would have gone to negative voltage, which means opposite direction. So figure 4.3.21 shows the rectified output voltage obtained from a diode when it is connected to an AC supply. So it helps convert AC to DC. And we're done with that. Congratulations. Right, I feel like we are making better progress, and so our syllabus hopefully would be completed by the target deadline. Any questions?
Mhm. No.
Okay, so do remind me the next time that we have some numericals to do, right?
Yeah.
And we'll do those first with electric circuits and components and all that, and then we'll move forward. Okay?
Yes.
All right, see you next time, inshallah.
Okay. Allah Hafiz.
Allah Hafiz.